Yeah, go ahead. Go ahead with your talk.
Yep. Okay.
You're good to go.
Okay. Right. Now I had it all lovely, well prepared, and this always screws me up. I'm sorry. I'm going to go try not to swear.
Don't worry. We won't blame you if you
Okay.
do.
So now what I'm on is, no, this won't work either. Ah, good. Okay. Right. I'm up and going now. The point about the 31 paper was that this is the paper which proves the Stone-von Neumann theorem, which says that the Schrödinger picture is unique up to a unitary. But what he does to prove it is he actually invents the Moyal algebra. Now, you might think this is quite crazy because Moyal's algebra was actually published in 1949, whereas von Neumann was working in 1931. But I was amazed to find that he had actually was using his creation of the Weyl algebra to actually prove this theorem. So the algebraic approach was being used by von Neumann to establish something in Hilbert space. And this is a very interesting paper. I found it extremely fascinating. So what does the theorem leave us? It leaves us with, by changing the gauge, by doing a unitary transformation, we can go from the Schrödinger to the Heisenberg interaction, Fock, or even the Dirac-Bohm picture, which the three of us actually published in Annals of Physics just recently in 1922. The point being there is that this gives us a gauge ambiguity. Second paper that influenced me no end was the discovery of Brice DeWitt's paper in 1952, where he looks at the Schrödinger picture in a Riemannian space-time. And what he finds is that you have to add an extra energy to the classical Hamiltonian before you convert it into an operator form. And the interesting thing is that this Q is very much like the relation to Bohm's quantum potential, which I was working on many years ago. But then there's also a gauge ambiguity in the Riemannian space. And this is well documented, and people who work in general relativity are well aware of it. And I want to bring that into the story. And in order to combine them, I then make use of Dyson's arguments that it was not necessary to have a complex field in quantum theory, but you need complex numbers. And for Dyson, the complex numbers came from the quaternions themselves. So what we're using is the basis vectors of the real quaternions. So we get 3 square roots of -1 now. So the roots of -1 come in the dynamics. So and the quaternion contains all the information contained in the Pauli wave function. The biquaternions contain all the information in the Dirac wave function. And this enables us to talk about probability currents, and we're talking about energy momentum flows or mass density flows. And that gets us into a situation which is close to what Einstein was talking about. In fact, Einstein crops up several times in my slide. Okay, so let's have a look. What did Brice DeWitt do? This is the paper which is lifted from PhysRev. One thing I want you to note about, I want to make a note of, the volume is 85, but then Bohm's hidden variable paper was 85. His paper was in volume issue 2, whereas Brice DeWitt's was in issue 4. I had been working with David Bohm for about 30 years, and he never mentioned this paper. This paper by DeWitt was not even mentioned in any of the discussions. And yet it's absolutely vital in the story of where this extra energy comes from, or what is this energy. Now, what Brice did was essentially to exploit the isomorphism between the group of contact transformations and the covering group. of the symplectic group. This is the unitary transformations in quantum mechanics, namely the metaplectic group. And what one then does is replaces the classical variables with the usual Schrödinger picture, but to ensure general covariance. Notice we're using the principle of general covariance. You have to add this extra term, which DeWitt called the quantum potential. Okay, how did he do it? Here we go. Here is the Hamiltonian standard quadratic form. You have to have a quadratic form in this. Then here's the extra term, h bar squared, and this is the classical potential. And then he writes the quantity h bar squared q may be regarded as a kind of quantum mechanical potential, which goes to 0 for h bar. It's a quantity which must be added to the covariant classical Hamiltonian in order to produce a covariant quantum Hamiltonian. And in a later paper, what he shows is that the extra term depends upon a scalar curvature. So somehow the geometry is coming in, and that extra quantum potential is related to the curvature of space. So one can have a sort of rough idea, where is that energy coming from? Well, when you go to quantum relativity, you have a mass equivalence, and then you have this relation rest mass, kinetic energy, and what's left over. Is what's left over got anything to do with this extra energy? I should just point out that actually Feynman, Schwinger, and Wheeler knew about this result. It was DeWitt was in the audience in the summer schools they had in those days, but they decided that the curvature was too small to measure. So it just got abandoned, and then the whole thing dies, and I'm not quite sure why it died there. So what did he do? Well, he looking at a relativistic spinless particle in a Riemannian space. I put pseudo there for the mathematicians. What you do is you replace the C numbers, the classical numbers, by Q numbers. So you're looking at the Heisenberg algebra. And then what you're doing is, because you don't have X and P, the eigenvalues existing simultaneously, you must replace the X and P in the algebra by these operators. But notice, you've also, if you're in the P representation, you have to use this representation. So the algebra is well defined, but the eigenvalues are not. And what you have to do in this space, we've now, the reason why you've got a Riemannian space is you've got a metric which is now a function of position. And even in a flat space-time, please notice that, in a flat space-time in the Schrödinger picture, you have to replace the operator for the momentum by this term here, and this is your old Christoffel symbol, and it's this term that turns out to be the quantum potential, and it's this term, and that's the way you see it related to the curvature tensor by exploiting that. And in fact, what one can do, and that's flat space-time, but what DeWitt also does is he looks at this on, he's got his little wave packet here, small extent, on a sphere. So he's now changing the metric so that you've got a curvature, you've got a curved space, and he then works through the wave packet of small widths. You get the, now, because you're dealing with the angular momentum phi, p theta and p5, phi, you've got the relation, you've got your operator relations, and what you find there is that the quantum potential looks like this, where mu is the rest mass. And then you've got the equations of motion, etc. And then he remarks that as h bar goes to 0 or mu goes to infinity, these equations reduce to their classical forms. He also has a discussion of the Pirani shield model, but then he says the quantum mechanical potential can be seen to be strongly divergent. So this is a problem that's coming up, but nevertheless, it must be retained for all quantum expressions in order that the Hamiltonian operator is invariant under the change of variables used to describe the gravitational field. That's very interesting. I don't know whether you folks find it very interesting, but I found it very interesting to discover something after all that time, which seemed to have been forgotten. And thanks to lockdown, I was able to do a lot of reading on my desktop here. And I started searching through the literature, and I found that this quantum potential, I've got quantum in quotes, and you'll see why. We have to look at it in a different way shortly. It's DeWitt. It was actually discovered, as you probably know, by de Broglie, but then Kennard in Phys Rev discussed it again, and then Bohm rediscovered it again. And this is all in spinless. But if you want to go to a spin and particle and relativity, then you're forced into Clifford algebras. And Clifford algebras come about because I got very interested in Clifford algebras because I used to listen to Roger Penrose in the early days when he was talking about twistors. And I only began to understand what he was talking about in those early days when I mastered Clifford algebras. It's interesting to note that Clifford was professor of mathematics at University College, where I am at the moment. So it's a little homegrown exercise, this one. Then the Pauli equation was already generalized by Bohm, but the Dirac equation Bohm found very difficult. And there is a story out there that Bohm said to someone that he would buy a crate of champagne for anybody who did the Dirac picture. But what he hadn't realized that the Dirac particle had already been done in 1931 by Schouten. And what Schouten writes is the most interesting result is the Riemannian character of space-time shows itself chiefly in diminishing the rest energy by this 1/3 K0, which is the curvature tensor, the scalar curvature tensor in Schutten's notation. And eventually I was able to, with the help of Robert Callaghan, to actually extend the Bohm approach to the Clifford algebras. Unfortunately, David had already departed, so I didn't get my crate of champagne. And what we showed was, and I just put these down to show you how they are related to each other. You've got the relativistic Dirac quantum potential, the Pauli quantum potential, and here is the quantum potential that those people who've seen the simple model that was talked about in our book, The Undivided Universe, and in Peter Holler's book. But you can do the same thing, by the way, for quantum fields. So what is the source of this? Well, let me quickly, I hope I can go through this quickly. What I call the most primitive Bohmian approach was just simply writing the polar decomposition of the wave function and then looking at the real part of the Schrödinger equation, separating real and imaginary from each other. And you see, it looks as if it's almost the same as the classical Hamilton-Jacobi equation. There's one difference. There's two differences actually, but the big difference is the appearance of this quantum potential. The other difference is that S is the phase, but in classical physics, S is the classical action. Okay, well, should that worry me? No, because if we recall Feynman's approach, what Feynman said was that in order to get a quantum field theory going, we have to sum over paths with this weighting factor. And what is this weighting factor? The weighting factor is the classical action. And in fact, what I showed in this journal in 2018 was that if you take a statistical average over the Feynman path, you actually find that the trajectories that you can get by integrating this expression, my next slide, I've actually got them in here, these, which you've probably seen, they actually are statistical averages of the Feynman paths. And notice all we're doing is we're just looking at the conservation of energy, assuming that this will give us the potential the momentum energy, and this will the momentum, which then squares to give us the kinetic energy. So here's the kinetic energy, here's this extra Q, here's the classic. So is this anything to do with the earlier expression I put up? Okay, well then you've probably seen these. This is what the quantum potential looked like when it's time averaged. When you're actually watching the wave packet approach a barrier, here's the time coordinate, here's approaching the barrier, there's the barrier, and you'll see what happens is with the individuals, some of the trajectories in the tail of the wave packet don't even get to the barrier before they're reflected. And these reflections are well known in optics. And this is why I'm saying we've got to be careful about whether it's quantum or not. In optics, these are called the Wiener fringes, and you can see them very clearly there. Never known whether these fringes have been seen for scalar particles or not. And then the quantum potential barrier at quantum potential is looking like this, where that's the barrier. Quite an extraordinary behavior. Okay, let me go on. Now then, another event occurred, which again rather surprised me. And this was a recent paper of 2013, not that recent, a paper by Michael Berry, in which he was discussing a classical scalar field. So this is where my doubts about the word quantum potential come in, because this is a classical theory. There you've got your wave equation, your classical wave equation, and you do the decomposition, and Berry this time, instead of using S, actually uses psi. Now in the optical case, A is just the this is coming from the iconal, it's just the refractive index squared, whereas the non-relativistic quantum mechanics, this term is just we usually see it in the square root, the velocity, giving you the square root of that. Okay, then what you do is feed them into the equations, then you find what was the quantum potential comes out to be the difference between this kinetic energy of the field, of the local wave field, and this AR, whatever AR is, that's put in there, that's the refractive index in the optical case, but it's the difference between the energy, total energy, and the classical potential energy in the case of the non-relativistic quantum mechanical particle. So what Berry gets are the two independent fields which are coherent, gets these streamlines like the Bohm streamlines, and shows that the curvature, the Gaussian curvature, can be written in this form, where this is the classical potential and this is the quantum potential. So that energy that DeWitt was talking about is now showing up in a classical situation as well. But it's to do with the geometry. So what this is telling me, anyway, is that we should be looking at quantum mechanics in a geometrical way and just put the wave function and Hilbert space to one side for the moment. Okay, I'll show you how you deal with that in a minute. Now, one of the troubles with the simplistic de Broglie-Bohm theory was that it was the key role that was played by the velocity, and in this game, in de Broglie-Bohm, that V has a B to it. It's the Bohm velocity, it's usually called. It is in the group I work with. Okay, but this depends very much on the potential, the nature of the potential. And if you go to a potential which is a 1 over R potential, what you find is you've got to bring in angular momentum. So the radial velocity should really be written not only with E minus V, but also minus the a term for the angular momentum. And in this case, mu is the effective mass. And this was known to Newton and also to Kepler, because you can get all Kepler's results out of this approach. But notice Bohm only discussed the velocity density. It's important to realize that when we talk, we should really not talk about velocity per se, but velocity densities. Then the velocity density, it plays a role very similar to the charge density. And in the charge density, you have the electric field, for example, in the electric analog. But what we're talking about in this theory is the mass current. And then, of course, the question is there equivalent magnetic mass current? And this is where Einstein pops in, 1917, and he suggests that we should have the magnetic mass current of this nature. And of course, this is just a rotating mass current. And it's going to be, if it's a mass current rotating, you're going to have some Coriolis effects. So this extra term that's coming in here is introducing Coriolis energies. I just pause there for a minute. This is going to be very important for us. Okay. Now, while I was in lockdown again, I read, once again, Weil's space-time matter. And Weil actually has a description of this Coriolis effect in terms of the geometry that he was inventing and discussing. And he showed that the curved flow lines, Singe made a very important contribution in this as well. The flow line, the energy momentum flow lines, resulted from two driving forces. When you looked at the accelerations, there seemed to be two driving forces for the flow. And Weil actually writes down what it is. Now, this is not quite the same as the DeWitt term. It's a Christoffel symbol, but it's a slightly different Christoffel symbol. But it's coming in because of the presence of a quadratic term. And what he found was that this quadratic term is just, he pulled it out and said, I'm going to call it F, and called it a Coriolis force. And then you've got an equation, acceleration of the mass accelerating, it's subject to two forces. One is the linear force and the other one is the Coriolis force. And that's well known in the force, in Einstein's general relativity force. The Coriolis force comes in left, right, and center. And I just wanted to convince myself that I was understanding what they were doing, but just very simply say, all right, best place to look at a Coriolis force is when you take your kiddie to the play park and you get him on the roundabout, he experiences the Coriolis force firsthand. So I've got a rotating frame, put it in the metric, keep the angular part of the metric flat. Then what I find is that you work through this, and when you work out the Coriolis term, it just gives you the third component is minus 2r omega squared, which is just related to the Coriolis effect. Okay, so it's cropping up there. And I want to make this just pause here. Here's Mr. Tompkins in Wonderland that got me interested in physics in the first place. Here is the Weil expression. Here now I put the Berry curvature expression. You'll notice it's in two parts as well. So what happens is in the steady flow, the kinks are acceleration, which split the momentum into two parts. There's a kinetic energy part, a scalar and that there is a second part, which David Bohm and I wrote a paper which we called it the osmotic momentum, because we didn't realize at that stage that it was actually tied in with what DeWitt had doing. Why didn't we know what DeWitt, why we couldn't tie it in? Because we weren't aware that DeWitt had done it in such a beautiful way. Okay. I'm sorry, I'm running a little bit behind. Is that all right?
Yes, that's fine, Basil. Don't worry.
Okay. Now then, what's this got to do with quantum mechanics? You're into general relativity, man. Come on, what's quantum mechanics? Well, it so happens that in atomic spectra, you can actually see the Coriolis energy in polyatomic atoms. And in fact, this effect is really in your gas meter. Energy crisis gas meter, it's using this Coriolis energy to measure the mass flow through your boiler system. But it appears in the polyatomic molecules when you have rotational degrees of freedom and vibrational degrees of freedom. And what you find is that the total rotating, vibrating energy levels has to have a correction factor, the Coriolis factor. And you can actually see the damn thing here. They actually show, so it's going to show up in quantum mechanics. So we better be aware that it's coming. Okay. Now then, in the opening slide, introduced, God, I do forget names so quickly, Dyson. Dyson was saying that we need the real quaternions. So now I've got to see how the quaternions come in. And of course, what I'm doing here is I'm heading for the Pauli and the Dirac equations. I've already shown you how the quantum potential comes in. I didn't tell you how I did it. Now let me give you some background into how I did it and what motivated me to go in this direction. And we've seen that we're dealing with a rotating frame, and we've got a rotating frame which we can bring in the fully fledged Riemann-Christoffel symbol as a Riemann tensor here. And what this gives you is a vector term, and for bivectors you use this expression. Now, that's not important. What is important is linearizing these quadratic terms. Now, what Dirac did, if you remember, when he saw the negative mass energies, was to say, oh, let me actually linearize my quadratic form. So I'm linearizing my quadratic form in this standard way. So I'm now saying that here are my flow line, my energy momentum flow lines. I'm taking V3 to be along the line in this case, and I'm looking at V1 and V2 as being perpendicular. Now, what we do is we've got that's a three-frame abstraction from this. I'll show you how I get it now. We've got, what we do to get the three form is we take Dirac's light cone coordinates. So we form E0 plus E3, E0 minus E3, E1, E2. So this V3 is going to be related to this term here, because this is about the forward light cone, and this is describing the backward light cone in your light structure in the Riemannian space. So I'm same thing goes over whether it's a mass current or whether it's a charge current. And then you write your quadratic form in this frame, in terms of these frames, and look what you've got. This is in fact just the Penrose incidence relation, and they're just quaternions. If you write these Pauli spinors in there for the quaternions, you find that this is just the quaternions over the real field. So to describe this moving object, i.e. in the forward light cone, it is just simply the quaternions that allows you to discuss this. Okay. Now then, what has this got to do with quantum mechanics? And this is really an important slide, which I was with two very bright research students who I had to spend a whole hour explaining what was going on. And I'm doing it here in 3 seconds almost. So please, I hope I can get the idea across. Remember, what we're saying is that we want to do everything in terms of Q numbers, as Dirac would say. And the Q numbers are just the algebra of the operators, but they're not operating on anything. They're just algebraic elements existing in their own right. In that algebra, you have things called minimum left ideals, and you write them by finding a primitive idempotent and then multiplying them by some function. And this gives you the minimum left ideal. Dirac already did this in his book on the principles of quantum mechanics, which we all read and all ignore. He introduces a thing called a standard ket. And this standard ket is not just the line, it's a very special ket, which is why he eventually put S in there. It's a very special, because it's the epsilon that comes in to give us the algebraic approach for the wave function. And the reason why I'm putting psi L here is because that psi L is going to contain all the information that's contained in the wave function, but in a geometric way. How come? Well, choose this particular idempotent. Then the Pauli wave function becomes the quaternion. So the quaternion that I obtained from the geometry comes out of the quantum mechanics, with the G's here are just the real numbers. And these are the bivectors rather than the Pauli spinors. How do I relate them? Very simply. The G's actually contain information about the wave functions. So I've got G0 giving me the real part of the wave function 1. G1 gives me the imaginary part of the wave function psi 2, etc. So this shows that there is a geometrical implication for quantum theory. And I owe my indebtitude to Ernst Binz for this. In his lovely book that he wrote with Sonia Podz, The Geometry of Heisenberg's Groups. Ernst is still with us, I hope, although I've not been contacted him lately. But he was very instrumental in helping me to understand this. Just let me put in, remember I told at the beginning slide was biquaternions. Well, the Dirac wave function is essentially a biquaternion, which you write like this. And these A, B, C, Ds, etc., are related to the 4 wave functions that we normally write as a column vector. Okay, so I hope now that you get the idea that I'm putting the information in the wave function into the geometry. And I'm using the quaternions in the case of the Pauli and the biquaternions in the case of the Dirac. And now Binz's work. Dear Ernst, we normally write the quaternions as a real field and a vector. But what we should do is split the quaternion into two reals, and write them in this form, where C and F are 2 independent spaces. Independent related spaces. In coordinate form, it means we take our quaternion, we have the scalar part and the vector part, but we now write it in terms of a complex number part, and this is also another complex number part if I take one of the complex numbers outside. So I'm combining 2 complex numbers in this whole story. And now this, I call this famous picture. It was drawn to me in a hotel lobby in Gothenburg in Sweden. The sea, what is the sea? Well, can you see the sphere there? I hope Ernst's pictures are clear enough. Put a light source just there. And the light source will then spread out. And this circle here is, or the sphere is the celestial sphere. And then we take a section through that sphere, and that defines my plane CA. Pull it out, here's CA, and I've got an E and an A there. Now, what that is I'm going to choose this direction of the light. You see, one of the problems is, where do I put this eye? Where do I put this eye? It's not a field there. It's coming from the dynamics itself. So it must be somewhere in the structure of the quaternion of this rotating sphere, whatever you want to call it. Well, you can draw A in any direction. So there's a whole field of A's you can choose. So what we do is we choose one A, and that defines what I mean by CA plus FA, because the FA is the tangent to the light ray. Okay, so what I've done here is I've broken the symmetry of that sphere, if you like, by choosing a particular direction to be my -1, so that I've actually got C itself is written in terms of 2 degrees of freedom. So if I replace, and what I'm doing here is, why have I brought in the light sphere? I'm using Dirac light cone coordinates. So I'm obviously talking about light sphere. And therefore, if I replace E, that's the scalar part here, by time, and the vector part in this picture will then be time and A will be E3 in the previous slides I've shown. So I've actually got a coordinate system in this pictorial system here, which talks about the forward light cone, and I've got one for the backward light cone. Okay, and what I will mainly talk about is the forward light cone, and then I'll show you why you need this backward light cone as well. Right, so now how do we put these things together? Well, I've got a series of pictures here which leads me on to the stereographic projection, because what these what the psi's are, they're essentially spinors. So I want to know how to relate these vectors v1, v2, and v3 to my spinors, and therefore to my wave functions. And what I can do is I can just put, and I'm using Penrose's language here, is my v3 is xaa dot in his terms, and it's just this quaternion here. And if we look at that in terms of the wave functions, once again, I get exactly the same relation between the g's and the psi's. And in fact, I can now write my v3, that particular vector, that's the light ray vector coming out of here. If this is a light, if we're talking about light energy coming out of there, then here is my my quaternion, and it's just the Stokes vector. Okay, well, now I can do exactly the same for the V1 and the V2, the perpendicular to V3, and I find that I can write that in terms of the following representation, which instead of using the complex conjugates, I use a dual relation. You can do this in SU3 because you don't have SL2C and SL2C star are in fact independent. You don't have that independence in the non-relativistic situation. What you find then is the vectors can be written like this. It's a complex vector, but it's a null vector. V1 and V2 are actually perpendicular to each other and perpendicular to V3. So we have a nice little triad for the electric component, the magnetic component, and that's the direction that the light ray is going in. So I'm already smuggled in electromagnetic theory through the back door. Now then, how is this related to Roger's flag picture that he uses? Very simply, here is the plane, here is his V1, and my V1 and V2 are down there. And what Roger uses is only essentially what I call half of this flag, half of the null plane. And a very good reason why he's using that is because he's going to the degenerate case in which you put x0 minus x3 equals 0, and then you just get your electromagnetic tensor to equal to V3 mu, V1 mu, and nu, and that is anti-symmetric relation there. So that's fine. But I'm doing the bigger version of it, and the bigger version of it, I'm just looking at the time. Okay, the bigger version of it, I'm not going to be able to get the whole thing done, Mike, I'm afraid. Give me an idea of when you want me to stop. Mike? Mike?
Yeah, we'll let you know, Basil. Keep going.
Okay,
We'll let
okay.
you know.
Can I keep going?
Yes, yes.
I want to show how...
Yeah, it's okay, Basil. I'm keeping an eye on the time. With the hiatus at the beginning, it's 5 minutes to. You can have another 15-20 minutes if you need.
Okay, that's fine. I'll get it done then. I'll get it done, I hope. Okay, so now what we've got here is a phase space. We've actually got a phase space on this disk. Now, how do I show that? The phase space, because I take the multiplication, or that should be a quaternion sign. I didn't have time to, I haven't changed it. Sorry about that. That's the quaternion sign. Mass BBH. We write so that K is the vector. Did I find it? I'm doing it a bit quickly here. The K, I haven't defined the K. The K is, oh yes, it is. The full quaternion can be written as a vector K. That's including the scalar part, the scalar and the vector part. And I want to write this product split it into two, essentially a Jordan product and a Lie product. So what I have is, if I do it that way, you'll see I have my, what was the electric current, and this was the magnetic current. So I'm getting that out of the Jordan product and a Lie product. So I'm putting together a Jordan product and a Lie product. Oh, sorry, yes, here we are. The K is defined as lambda times the scalar, and U is the vector part of the Hamiltonian, of the Heisenberg, of the quaternion. Okay, now doing it this way, the Jordan product already contains a way of dealing with the metric. And I can just take the Jordan product, and that shows me that I've got the metric present. So once again, I'm putting together two bits of the quaternion, one to give me the symmetric metric, but the FA contains a natural anti-symmetric 2 form, which we've already seen as that. But in fact, if you go through Bintz's work, and you can show that we can define your 2 form in terms of the 2 H vectors. Those are the vectors in F. I've been calling them V, and I've now changed to H. Sorry for the inconsistency. But they are essentially the V vectors. And so what I've got is that my elements are now giving me the vector current and the bivector current without actually making the effort to do it. It's already in the mathematical structure using the quaternions over the reals. So what this means is I've got the symplectic and the orthogonal together, and that's what we need to make the DeWitt work, the DeWitt story hold water, is we're putting together a symplectic structure and an orthogonal structure. Okay. And this, I'll leave that slide out because I want now, so far, I haven't gone back to the ambiguity, the gauge invariant, the gauge, and this is one of a very important ideas that I developed in lockdown. I've seen it lurking around in other people's work, but I've not seen it combined quite like this. If someone else has done it before me, please would somebody tell me? The point being that when we're using the differential geometry, which is the basis of everything I'm doing, the partial derivative is not a tensor. That's why you have to add to it Christoffel symbols. They aren't tensors. So you add a couple of non-tensors together to get a tensor. You really should go directly to the covariant derivative. Now, we physicists like our wave equations to be quadratics in partial derivatives, but we must write them if we're strictly going to maintain general covariance. We must write them in terms of covariant derivatives. But what one should notice, physicists love coordinates. But under a coordinate change, this quadratic term is not equal to that quadratic term. There is a difference between them. And this difference is summarized in this C-vector. All of this is discussed in Robert Volt's general relativity, by the way. There's a tensor there. And that tensor is playing an important role. It's where the gauge ambiguity comes in. Because what we can do is we can conformally rescale and we can express this tensor solely in terms of the metric and the covariant derivatives. So we don't have to bring it in via the Christoffel symbols. We bring it in this way. But how does a scalar curvature be affected by conformal rescaling? Well, after a lot of hard work, you'll find it all worked out in Robert's book. Your scalar curvature in the new coordinates is related to the scalar curvature in the old coordinates by this long term here. Okay, so we see there's a gauge ambiguity and it's thrown up in the scalar curvature. But what you can do is you can go to, can you see this? Oh, there's something there that's missing. Let me bring it. Okay, good. Right. Very important term, this. If you are using an equation like this, you want to somehow get the change in gammas compensated for by the change in the phi. And that's exactly what we do here. Under the gauge transformation, you have to change the wave field in some way with an omega, and omega, remember, is this conformal factor. At the moment, I've just put S in there, but what Robert actually works out for us is that if we go to go through all this rigmarole, we find that S is actually equal to 1 minus n over 2. And if n is 4, 2, that's S is just 1. And then when you put the 1 in there, you get the curvature, you get this expression for the energy, for the Kline-Gordon equation, zero rest mass Kline-Gordon equation. So this brings us back to DeWitt again. Okay, now then, what's it got to do with us? Is the Bohm's Q identical to the DeWitt's Q? Interesting question. Under the conformal scale transforming, we had in that previous slide, which has been badly presented, I'm sorry, but it was the omega minus 1. When you put this, when you put this in, I'm sorry, I did the calculation wrong. It's minus 1, not 1. I think I said 1. I'm sorry. I can get my head around all this difficult stuff, but I can't do simple arithmetic. So we've got omega minus 1. So now what happens to the Schrödinger picture? Because I'm interested also in, because DeWitt was in the Kline-Gordon, but what about the Schrödinger equation? How does the Q show up? How does this curvature, how does this effect show up in? Well, then you've got to go to what I call the Dirac-Bohm picture, was why we actually introduced this picture in the first place. And this picture was simply, instead of using the Schrödinger picture, we used the picture which was depends only on the exponential, so that we leave out the amplitude part, and we'll get a perfectly good description of the, but we've got to take into account the fact that we haven't brought the R in there. And if we use this omega minus 1, we see that the amplitude is in fact equal to this factor, omega. And then when we go through the rescaled flat, notice Minkowski space-time, the curvature tensor becomes all this, just pure mathematics, just plugging in. If we now put in omega equals R, we get this expression here. And if we, but we know the quantum potential, the relativistic quantum potential is this. In the non-relativistic limit, it goes to there. In the relativistic limits, it's the D'Alembert R over R. Put that in there, and there you go. So we've now explained exactly where this term comes from in the DeWitts, and it comes through the amplitude of the wave function. The amplitude of the wave function is not a wave. Don't look at it that way. It's totally puzzling. When we got this result, I thought it's crazy. But no, what's crazy is the wave function. Okay, and then we get that right. Now then, final slide. Let's go right back to de Broglie, 1927. And what he did was to write the generally covariant equation, and he stuck in the rest mass squared there. But then when he realized that if you do the real part of this equation, it suddenly becomes an extra Q comes in here. So what de Broglie said was, let's write the Kline-Gordon equation as that equals capital M squared C squared. You see, the de Broglie work was nothing to do with the pilot wave, nothing to do with the Mickey Mouse guidance condition. It was about energies. And he regretted in his book on nonlinear wave mechanics, you'll see, he says, I wish people would not associate me with the pilot wave. I introduced it, and I damn well wish I hadn't have done. He doesn't use my language, but you can tell that's frustration coming through. Okay, and then here is the quantum potential. So this means that the mass has this extra term in it. So you see what's happening, where the conformal rescaling is actually playing around all the time with this quantum potential. And this extra quantum potential in the Kline-Gordon equation becomes the Bohm quantum potential. Okay, but now you'll notice something very interesting, which I thought I'd done something boo-booed. Suppose we do the conformal rescaling so that we turn m naught into little m naught into capital M naught. And then what you find is, look, here is the conformal scaling factor. It's m naught squared. So it's m naught over big M naught over little m naught all squared. So the omega is the little m naught, big M naught over little m naught. And in this case, the rescaling factor is this. Alarm bells. Not to worry. When we were using the Dirac-Bohm picture, we were actually not very far away from the Schrödinger picture. What Dirac was doing was leaping to the Heisenberg picture. And in the Heisenberg picture, you will find that you've taken all the time dependence into the operators. The wave function is just an initial condition. Schrödinger, the wave function depends upon time. So this term is in there, but in the way of looking at it through conformal rescaling, it's outside. So you have to add this extra term in the Heisenberg picture. So what DeWitt was doing was actually using the Heisenberg picture, but the whole thing becomes very much more simple if you forget about wave functions and do everything in the algebra itself. If you do everything in the algebra itself, you don't get any collapse of wave functions. And I just want to leave you with some numerical work that Peter Van Rieth did. It was done by Chris Dewdney originally, but it's to illustrate how the quantum potential comes in a very simple, naive model of a spinning top. You find that the translation quantum potential is the usual one, but there is a spin quantum potential. So there is a coupling of the spin, and the coupling of the spin is most beautifully illustrated in a Stern-Gerlach magnet. Here, this is a simulation by Peter. Here is where the magnetic field is all congregated. There is no field outside here. Yet look, spin is all coming in this direction, and you're using this to prepare spin up and spin down. In this picture, there are no quantum jumps. The spin smoothly goes into spin up, smoothly goes into spin down. So there are no jumps, there is no collapse of any wave function. I just leave you with these last pictures. We've got two Stern-Gerlach magnets here. We're trying to put them together again, and look what happens. And this is what we're trying to get an experimental handle on in the work that Rob Flack and Vincenzo Monticello and other people are trying to do at UCL at the moment. Okay, folks. Thank you, Mike, for letting me do that.
Thank
Well, that's
you,
quite
Basil.
okay, Basil. In fact, you only it's only just 10 minutes past, so taking into account the hiatus with your slides and my introduction, I think, in fact, you did, in fact, speak for pretty well exactly the hour. But that leaves us with plenty of time for Q&A. Let me begin by thanking you for an extraordinarily, vastly wide-ranging talk, obviously bringing in some very original and powerful and startling ideas, such as that, we don't really need wave functions to do quantum mechanics, for starters. And with hints of all sorts of other fascinating connections, I'd particularly like to hear a little bit more about how the conformal rescaling and this picture of the spinor connects up. Well, in fact, you touched on it when you said that Roger's picture of the twistors, from your point of view, only really uses potentially half, I should say, the potential strength of the structure that you're introducing via the Quaternions. I was going to ask if you could say a little bit more about that, but it is not for me to ask the questions. I'm supposed to be chairing. So let me ask Tejinder. I haven't had a chance to check chats. Do we have anybody on the chat who has a question ready to ask? Yes, we do.
On the chat, I don't see a question yet, but thanks,
No.
Basil, for a very beautiful lecture, and which we'll hope to put on the recording within a few days. So
Yes.
please, the talk is open for questions. Kindly go ahead.
Yes, far away. We've unmuted people, have we? So people can now ask questions.
Well, you should get them to put their hand up.
Right. Well, I have a question here from David Chester, who's one of our following us online, who says, in what sense are the split-Quaternions related to symplectic structure?
Oh, okay. Well, I think I can do that by going on to the, you wanted me to clarify that, did you? Let me see.
Well, that was David's question, I think.
Yeah, no,
Yes,
I think
please.
it's
Thank you
important.
for
It's
the
an
talk.
important question. No, it's an important question. Let me see. I'm just trying to get through to the slide because I find it much easier to talk to the formulae. Yeah. So just let's come in. No, that's not doing it. Where do I do it? Trouble is, I've got bad eyesight and I can't see.
Sorry, there are some further questions coming from David.
Yeah, okay, wait a minute.
Would David, you're unmuted, so you can read your questions out.
Awesome. Yeah, I was just sharing a couple links, but yeah, overall, I'm just curious about the relationship between split quaternions and symplectic structures that you mentioned.
I'm not sure. This is where I think I introduced it more directly. When I introduced the whole idea was, first of all, do you take the idea of the Bint's idea of splitting the quaternions into 2 + 2? Because that's essentially what we're doing.
Oh, okay. So by split quaternions, do you mean quaternions
let's
split into 2 complex numbers?
Yeah, this is the naive way of starting it. And then you go in to Clifford algebras and you've got the triangle of all the product rules. No, it's not the way to do it. Ask me a question from here and let's see if we can get to the bottom of your problem.
Well, okay, here you mentioned quaternions, I believe.
Yes.
So I suppose it's worth clarifying that there are 2 different algebras, the quaternions and the split quaternions. I believe on an earlier slide, very early on, you mentioned that there was 2 applications, one being quaternions and one being split quaternions.
Yes.
And so I guess my question was more related to the split quaternions, whereas this, you are taking the quaternions and separating into 2 complex numbers.
Yes, but then it's the way I put them together that the symplectic structure comes in. And that is here where I'm beginning to distinguish between the Jordan product and the Lie product.
Okay, so is it just the quaternions that are used for describing this symplectic structure you had in mind?
No, you take the quaternion structure. What you've got to do is to do 2 things. You've got to bring together the orthogonal structure, which comes out of the Clifford algebras, but you've got to bring out the symplectic structure as well. Because what we're really interested in the physics is the overlap between the symplectic and the orthogonal, and that's where the unitary groups come in.
Very nice. Yeah, there was some work by Bertram Costant on that as well, by the way.
Sorry?
Bertram Costant had some work on SP8R intersected with spin 4,4 to find 3 conformal groups, for instance.
I'm sure, but this is my way of doing it. Yeah, I'm well aware of that. Yeah.
Please use the raise hand feature. If you have a question, then I'll unmute you and you can.
Okay, thanks for the feedback and thanks for the talk. I really appreciate it.
Thank you. I hope I've got the idea across.
So,
thanks to David.
Basil, maybe I can throw in a question.
Yep.
So I heard a recording by Michael Atiyah where he says that the Dirac operator was in fact first discovered by Hamilton when he discovered the quaternions, because if we think of a gradient operator on the quaternionic space, it is the Dirac operator. Does this look reasonable? Could you say a little bit more about this?
That is what would happen if you looked at what I was doing a little bit more carefully in terms of taking the linearization. You'll find it works that way.
Okay, so the gamma matrix.
I don't think it gives us any more physical insight, but it certainly certainly confirms what you're trying to say.
Yeah. But it just means that the gamma matrices are a trade-off for the quaternions. Instead of quaternion, if you use the Minkowski space-time, then you have to put in the gamma matrices by hand. But if you're working with quaternions right from the start, then you don't need gamma matrices. But that's very fundamental. I would like to think of space-time or the square root of space-time as being, made of quaternions and not, the Minkowski differential dt, dx, dy, dz. I can make spinors from the Clifford algebra coming from the quaternions, and I can start making, say, for example, lepton states, a neutrino and electron states from these spinors. And then we see that in this sense, the quaternionic picture is more fundamental than the Minkowski picture, insofar as the Dirac operator is concerned, because it directly lets me inevitably construct states for leptons.
Yeah. Yes, you're quite right. I mean, I think this opens up a whole host of questions. What are the geometrical implications of the symmetries that people are discussing in elementary particle physics?
Right,
the reason for why I'm emphasizing the mass is because in there, I'm sure somewhere there's a clue as to the mass spectrum. I don't know what it is, but I'm dealing with the flow of mass density. And therefore, it must be in that flow. And in that flow, notice that energy, you've always got to have energy conserved. So if you think about it, this is an example that Penrose gives in one of his books. As you move the particles apart, you find that with the gravitational field between them, the gravitational potential energy increases. So where does the energy come from? If it's an explosion, say, moving that way, it comes from the rest mass of the particles itself. So the rest mass is being converted into classical potential in that case, not quantum potential, just classical potential. But then there's not very much difference between robotics, for example. The robot engineers use the quaternions because they're interested in the relation between the rotation and the translation. And you want that movement. I don't know if you can see my hand waving around, but that is something which is much easier to put on the computer than to go through the Minkowski space formalism.
Absolutely, absolutely. So one more
we
question.
have a question. Jens Koplinger has been waiting for some time with a raised hand. So can I bring him in now, please? Sure. Jens.
Yeah, thank you. First of all, thank you for your talk. That was great. Also, I love your references in the 1930s and before, which seems to be the perfect time to look at for what you're doing. I have a question about your slide 11 in particular, about the masses there.
Okay, let's have a look. Where's 11?
Yes, sir.
Yes, you've gone past it.
Oh, yes.
Okay, yeah, there you are.
Yeah, here you go. I'm trying to understand that the picture on the right. What are those M1 and M2 again?
It's how do you do the Kepler orbiting problem, where you've got two masses that are gravitationally rotating around each other?
Okay.
Okay, that's what I meant to show with that. Okay. And then what you have is you must have a conservation of energy. So you go to the difference, so you change everything to the difference between the two masses. So that's talking about what I was just saying to just in the moving them apart. In this case, they're going to be moving around each other, so they move around their center of mass.
And so what is missing in your view in the simplistic Bohm approach then?
Well, because because what one has done there is introduced the grad S alone. Okay, there's no angular momentum in the Bohm approach.
Okay.
Yeah, it's only because you haven't just opened your eyes a little bit and said, well, what happens if we're dealing with something which is rotating? Because that's all right for some linear potential. But if it's a rotating potential, if it's a 1/r potential, rather, sorry, that gives rise to a rotation, then you've got to bring in angular momentum.
Okay.
And
Okay.
then it's very simple. If you come through the quasi-classical approach, you know, it's shows what's missing. And all the way through the talk, I hope I've made it clear that there is this electric type and the magnetic type of force.
Yeah, very, very, very cool. Thank you very much.
We have a question from, is it Richard or Rick?
Yes, Richard
Dawson.
Clausen. Thank you.
Yeah, right.
Following on the same slide, so this bringing angular momentum into this is very interesting, and I'm wondering about the possibility, if you consider a particle not with just orbital angular momentum, but spin angular momentum, could that be related to?
Well, I've actually sneaked it in later on without you realizing it. Yes, it's very. Look, I had an hour to get all of this in.
Right. Okay.
And certainly, this is just the beginning. This is where I started with something simple that we all know, or we think we know what angular momentum is.
So
And
could
then,
the spin, does the spin angular momentum end up being related to the quantum potential?
It gives an extra potential. That there is, the spin has a coupling to it. And that coupling is shown up in the quantum potential. That was the second part of the quantum potential, almost at the very last slide I had. Let me get to it here. So what you've got, this is the quantum potential for the linear transformation. And this is the transformation, and this is actually acting on the spin. So I've sort of sneaked, I've jumped in without, probably you didn't realize where I'd sneaked it in, but I only had the hour, so I.
Yes, okay, well, that's good. I thank you for your answer and for your talk. It was very interesting.
Good, thanks. Well, thanks.
So Basil, what would compel us to go to the octonions?
Well, that's an interesting question, because I used to work with a guy called Clive Kilmister, who was at King's, and he was an expert on non-associative algebras, and he frightened the pants off me. So I always put the quaternions to bed, as it were. I didn't want to know anything about it. But I think now that I've got this, I mean, I hope you realize, Jinder, this has only become clear to me in the last 2 years.
Mm-hmm.
In the previous years, I would not have been able to give this talk because I didn't know anything about it.
Mm-hmm.
So, but now I have clarified exactly how the split of quaternions come in. Now but that's all in the Clifford algebra regime. This is the interesting thing.
Mm-hmm.
And now when we go to the octonions, we go outside the Clifford algebra. I think I must raise my eyes and say, well, go on. You're probably outside it already when you've done something by taking the overlap between the orthogonal and the symplectic as being the basic structure that you want. You see, the Clifford is all rotations, and the metaplectic, etc., is all the symplectic. But there is a common overlap in the dynamics of those two. Now, at the moment, I don't see how to generalize it to the octonions. I have to look a lot more carefully at how the twistor comes in, because I didn't present it here in this talk because I don't have time. But when I was looking at the twistors way back, before I had this latest stuff in my mind, way back with David Bohm, we actually showed how you could do what Roger was doing with his twistors with the Dirac matrices. There's a paper we published in the Reviews of the Brazilian Physical Society in honor of Mario Schoenberg, because a lot of these ideas I learnt in the very early days from Mario Schoenberg's work in Brazil. Very important work where he actually introduced the connection between, where he pointed out that there was a connection between the symplectic and the orthogonal. But the trouble was, I kept seeing it as a product, but it should be as an intersection.
Yeah, it's the intersection.
Yeah, it should be an intersection. Now then.
Sorry, do you have a reference to that paper in here, or could you provide one?
Which paper
Which paper
do
you're referring to in the Brazilian journal about the Dirac
Oh,
matrices?
yeah, it's 1980. Just a minute. I can give you the actual reference if my computer will allow me to do it.
If I can say quickly about what I think we'll do, Basil, is to put a list of all your references and indeed all of your publications, including the Revista Brasiliana one, on the website, on the chat, which we'll attach to the recordings when we put them up.
Okay, well, it was 1980. Well, make sure that one's on there, Mike, for me, please.
I certainly will, yes. That's an exceptionally interesting paper. This is the first time I became aware of this entirely distinct, I don't want to say opposed, but certainly quite distinct approach to building up the twistors, essentially from starting really from real field rather than by laying the emphasis, which Roger does in his approach, on the complex analytic structure.
Yeah,
and very interesting because they both complement one another. But it does seem at the end you've made the very interesting point. Of course, I don't pretend to any kind of specialist knowledge of twistor theory, and I'm sure there's a huge literature out there that I'm unaware of. But the insight that in this approach you do essentially get sort of a dualization. You get twice the strength really of the of potential strength of the flag picture than the part that Roger uses, and I find that very, very interesting.
Well, there is some extra structure that I use. That's
yes, so that's about yes.
Yeah. So
but then don't forget, Roger is actually working with light rays. A lot of his emphasis is on the structure of light.
Well, yes, because he's trying to recover the Minkowski structure, of
yes.
course, is essentially trying to in a complexified form. It's But
the interesting thing about the twistors was that when I analyzed it to find the minimum idempotence, I found that the minimal idempotence for both the twistors and the Dirac spinors are identical.
Yes, that was the connection with the Dirac spinors. That was very interesting. You were saying that you could do everything.
And that was the one that, but that's another talk, Mike. You really
no, I know that's exceptionally interesting. That also connected, I think, with some of the work that you did with Fabio Frescura about the the deeper meaning of spin from the point of view of these algebraic structures in phase space.
Yes, yeah.
And in which way you kind of recover the twistor. But the point about that was, as I remember, that the framework for that generalization was very much the Clifford algebra framework, because the twistors naturally emerged as the not the topmost, but the one from the topmost structure of in the eightfold Bott periodicity, which you get within the Clifford algebra. And once you go outside the Clifford algebra, of course, you've lost all of that constraining structure. So once you go non-associative, which I think it may be a reason that you hadn't been tempted down the octonions route until this point, though of course that may be changing.
Well, I'm not going to reject it, because there is the triality idea in the Clifford algebra, which is closely related to the octonions.
Yeah.
And I have to go through that again. I'm sorry. You see, Tajinder, I actually was looking at the symmetries E8 cross E8, etc. in the 90s. I never published anything because I just felt I didn't have any principles to guide me. It was a bit like pinning the tail on a donkey when you're blindfolded. You know, you just sort of say, well, will this do? Will this do? Will that do? And I felt I needed some general principles in order to restrict the structure.
Yeah, so what I seem to find with my students is that when you're working with E8 cross E8, it helps to associate one of the E8 with the left-handed fermions and the standard model, and the second E8 with the right-handed fermions and gravitation, a generalization of gravitation, where there's a U1 charge, which is square root of mass. For the left-handed fermions, the UN charge is the electric charge, but for the right-handed fermions, it's square root of mass. So it's as if the two E8s are coupling, linking the standard model to a gravitation, but in higher dimensions.
Right.
So there I wanted to ask you that instead of starting with a 4-dimensional space-time, suppose you had started with a 10-dimensional space-time, Minkowski space-time, would you have landed up with octonions instead of the quaternions?
Not the way I was doing it through the Clifford algebras. I mean, I've actually, if you build up the tower of Clifford algebras, the fantastic little image that I suddenly drew up was, you see, the question is why did Clifford in 1880 something come to his algebras, which we use for spin? I mean, this is an incredible question that was crossing me. It's got, so really the Clifford algebras have got nothing to do with quantum mechanics in that sense. They're actually there already in classical mechanics.
Mm-hmm.
They do, of course, come very much from this investigation of an inherently dynamical geometry, where you have the rotate, not just translations, but rotations and all the other operations.
Well, please, Mike,
built into the algebra.
What Dirac, if you read Dirac's book on the exact mathematical sciences, I think it was a set of notes which someone put together after he died. He starts his Clifford algebras with trying to give people a direction to go to the local pub down the road.
That's right, yes. Is that Dirac?
Hey?
Really?
No, Clifford.
Oh, Clifford. Oh, yes, yes, I believe it's Clifford.
Clifford.
Yes, I'm sorry. I never thought of Dirac as much of a pub goer.
No.
Clifford, I believe, was.
No,
yes.
Sorry, I hope I didn't say Dirac.
No.
I meant Clifford.
Yes, no, Clifford. That's quite all right.
And then Clifford, out comes his language, which is the Clifford algebra.
Yes.
And the Clifford product, for instance, which is the which combines the exterior product and the inner product.
Yes. I mean, he was obviously, amongst other things, he was trying to make sense of the developments which had come with Grassmann and with Hamilton, particularly, as I said, in understanding the relationship between the interior and the exterior product. But I think it was bringing in rotations that I think gave him the idea from the next stage beyond the trick of how many times is it where you have to turn back on your in order to get to the
but
pub.
I think, in fact, I'm sorry, I forgot the gentleman who asked me about sorry, something's gone again. He asked me about the symplectic structure.
That's right.
David Chester.
Yes, David. And I think he has another question, actually. So we must ask if there are some more people in the room.
If he reads that book, he'll begin and realizes that what you're actually doing with the symplectic algebra is you're conserving areas.
Yes, yes.
And that's the most important thing, you see, you're conserving areas. And it's in the conservation of area that we get things like the Gromov's no squeezing theorem, for example, which is in classical physics as well as in quantum physics. But in quantum physics, you cannot squeeze the area below h squared.
But
H
so,
bar squared.
well,
Sorry.
what do we make of the group theory relations like SL2O is related to SO19, SL2H is related to SO15? That must have the same kind of implications as the SL2C.
Yeah, I'm sure you're right, but I did all that malarkey before I understood what I've understood now. Maybe if I go back again, it'll show that those connections in a different light.
Okay. Thank you. Yes.
I mean, I'm sure there's some bright youngsters out there who should be looking at this kind of thing.
Yeah. So it's like if you take the octonionic space as an extension of the quaternionic space, then the gradient operator on that space looks like the Dirac operator in higher dimensional space times, possibly 10. I mean, that's one guess.
Yeah, but I'm very much taken with Roger Penrose's idea that you don't really need more than 4 dimensions. Once you go above that, it seems rather artificial. I mean, I'm often wondered, you see, I grew up working on the Ising model, and I was doing particularly the Yvonne model, and I was looking at lattice gases and things like that. And I found that in order to understand the energies, you had to understand how clusters work, in fact, it comes down to finding knot structures. And in those knot structures, you know that knots in higher dimensions are not knots anymore, they just untangle. And therefore, I feel that somehow there's something special about 1, 2, and 3, and maybe 4, and 5, 6, and 7 is nothing special anymore. Now maybe I'm wrong on that. I don't know.
Yeah, I think it might become a little less demanding if we think of, the gauge fiber bundle, like we were talking to Roger last time. The fiber bundle defines a space which might be thinkable as an extension of space-time. In many ways, the weak interaction in particular looks more like a space-time symmetry than like an internal symmetry, so that weak and gravity together have something to do with 6-dimensional space-time, with the weak force bringing in 2 additional space dimensions, and then 4 more space dimensions for the strong force. So not so much in the sense of thinking of a 10D space-time, but sort of unifying the fiber bundle space with the 4D Minkowski space-time.
Yes, my worry about the fiber bundle is the local product space. So that's fine for dealing with the complicated classical system, but when you've got a problem with, particularly with phase space, because I hope you realize that what I've been doing is working mainly in a non-commutative phase space. And all these properties that I've got out are coming from that non-commutative structure.
Right.
And that is a very rich structure, which has a lot of interesting features to it, which I'm only just beginning to get hold of. And So when you sort of just generalize the fiber bundle, I begin to worry, but wait a minute. If you really take seriously this non-commutative structure, then you've got to build in your non-commutativity right from the beginning. And the only way I see of doing that at the moment was the way Dirac was doing it. And that's to think of everything as a process. I'm sorry, I'm going to bring in some philosophy here. It's a process of how one goes, well, how particle A gets to particle B and what happens as it's going. It's the process that is the important thing. And that's very much what Dirac was saying. It's the process of how do you get to the George. It's the process of how do you introduce the symplectic structure.
Mm-hmm.
You see, and I think just looking at the fiber bundle, you're missing all that notion of process. I'm much more interested actually in the way the category theory boys come to this.
Mm-hmm.
It fits in much more with this, but they have got nowhere near the elementary particles yet, you see, and that's what's missing.
Yeah, so what I saw, I could be wrong. Suppose you take a split bioctonion, which defines a 16-dimensional space, and then you try to make a quadratic form from here. It comes as a sum of a Euclidean section and a Lorentzian section, both of which are higher dimensional. So that's what made me think that maybe the split bioctonions might provide a way of thinking of the fiber bundle and the space-time in some kind of a unified picture.
And can I ask where does the non-commutativity come into that in the octonian structure?
I mean the octonion multiplication itself. That's not good enough, is it?
No, that's fine. If yeah, that's fine. That's fine. And I was just wondering about no, we'll let it go. We'll let it go.
Okay,
No.
yeah. Thank you.
I really bow to your superior knowledge of the
No, please forgive me. Don't say that. You have looked at it more deeply, yes. Yeah. Actually, if there were no further questions coming, oh yes, there's a question.
Sorry to interject. Can I just interject very quickly here? There are a couple of we must preserve the chat. I think if somebody can press whatever is the button needed to preserve the chat. There's a reference here. I think it's from David Chester. A footnote to his very interesting question. He mentions, well, can I just read it out, perhaps, with his permission? Just a comment in relation to Berry's work. You spoke about Michael Berry's work in the course of your talk. Perhaps classical field theory should not be second quantized, yet be first quantized and still contain H bar and a quantum potential. And then he goes on to give a reference, which actually I think may perhaps go to your point about the attempts which the category theory people are making to try to investigate some of these algebraic structures, although they haven't got anything like as far as the issues about the particle spectrum yet. There's a reference to math stack exchange. Stack exchange is a site which has a lot of exchanges which have fueled my category theory notions. There's specifically a reference here to a paper about the intersection of the orthogonal and symplectic groups in even. Well, unfortunately, I don't see the rest of, possibly because the title of the abstract is cut off. But it actually contains a specific reference to the intersection of the orthogonal and symplectic groups. And it's in math stack exchange. It's in the chat if anybody wants to save the chat. And there are several other very interesting comments in the chat. Can I ask if there's anybody else in the chat room at the moment from amongst our participants who would like to ask? Basil,
Jen has a question. Jen has a question
there.
Yes, okay. Please go ahead.
Yeah, thanks. Yeah, I was waiting since it goes a little bit a different direction. On your slide 24, I have a question for that, if you don't mind.
Yeah. Oh,
yes.
It's De Broglie, yep.
Yeah, so this is very fascinating. The first 3 lines there. So I see. So de Broglie. So he started with a generally covariant Kline-Gordon equation and then put the de Broglie terms in there, which you motivate from Bohmian mechanics. And I'm just wondering, and I may look at that over the next year, whether you could start with a specially covariant Kline-Gordon, so not generally covariant, just special, and then work in not just the quantum terms, but also terms to then reconstruct linearized gravity from that. And then the reason why I'm contemplating that is, linearized gravity, you have linearized potential, and Bohm's de Broglie, you have linearized. So it seems like an easier starting point to first do that, and then later bootstrap up to generally covariant through field self-interaction.
Yeah, well, I came through the general covariance because of Brice DeWitt's paper. Suddenly it opened up. This is one way to look at it.
Yeah. No, this is fascinating, huh?
Yeah, but then you see, lurking. I think what I've got here on this slide is probably taken from a discussion in de Broglie's later book, the nonlinear wave mechanics, double solution.
Okay.
That's if you're interested in this, that's a fascinating book. You can read it either in French or in English. There's an English translation.
Okay, thank you. Thanks for the pointer.
Yeah, and that is where de Broglie actually criticizes his own potential, his own guidance condition. He thought the pilot wave was not very. He wished he hadn't have sent it, actually.
Okay. And how is that book called again, or what year is it roughly?
I'll
find it, but.
Yeah, it's 50. Is it 60? It's 56, 60.
Okay. I think you mentioned it was 56, Basil.
56,
it's about 30 years after his original work.
I mean, I know I've got it here somewhere. Oh, wait a minute,
Okay.
I can tell you, I've got it.
All right, thank you.
And it's called Nonlinear Wave Mechanics.
Okay.
And I think it then a causal interpretation.
Yeah.
And
thank you very much.
Published by, it's about 1960. It's
Right.
1960.
We're out by a few years, but still.
Well, I always say 56 plus or minus 4.
So we welcome further questions, please. We still have 10 minutes at least. Basil, could I use this opportunity to talk a little bit about Bohmian mechanics with you?
Yes.
Yeah. So one of the two things I wanted to ask you. One is the Bohm rule sort of derivation or interpretation is related to the initial conditions being what's called typical or satisfying a quantum equilibrium, as opposed to a quantum non-equilibrium. I've seen Anthony Valentini talking about this. What exactly is a quantum non-equilibrium?
Well, you better ask Anthony, because I'm not totally clear on what he's doing there. But he's trying to say that there may be situations in which the probability rule doesn't work. I mean, I think David Bohm already did something like this with Vigier on the stochastic process, where he actually looked at the situation where when you disturb the system via a measurement or something, there are non-linear terms which actually collapse in the stochastic background, which force the particles to come down to an equilibrium situation, i.e. the Bohm probability rule holds.
Okay, so was there ever a situation like in a quantum non-equilibrium, the Heisenberg algebra Q p equals IH bar does not hold?
No, what I've been talking about here is always closed systems.
Okay.
And therefore we've got rigid conservation of energy coming in. But if you feed in energy from the outside, that's another story. Very interesting story.
And in quantum non-equilibrium, might you be able to have non-local Bell correlations stronger than what you have in quantum equilibrium?
I really don't know. I mean, to
I think
me,
Anthony Valentini has speculated precisely that, has actually put that speculation out there. I'm not sure he wants to positively endorse it, but he has suggested that his framework would make room for that, if I've understood his work.
Say it again, Michael. Room for what?
Well, no, but that it would allow for Bell correlations larger than those which and I think it's all to do with the way that Lorentz invariance is basically compromised in this non-equilibrium picture. You no longer have a Lorentz symmetry in the I can't speak for Anthony Valentini because I haven't read his work carefully enough. But I do know people in the philosophy of physics group in Oxford who are very close to him, and I've heard him talk on this on a number of occasions. If I've understood, he's proposing a kind of cosmology in which in the initial state there is this non-equilibrium dynamics, which
so suppose I want to
involves
try to make a quantum non-equilibrium system in the laboratory.
Yeah.
What would it look like? I mean,
and there I'm afraid I have got no intuition at all about what he thinks, except that somebody once trying to sort of somebody once tried to pin on him the suggestion that he really wanted to take us right back beyond Galileo, right the way back to Aristotle in terms of his understanding of dynamics. With the implication that this was really a very kind of retrograde conceptual move. Of course, he resisted that suggestion, but no, I think that's a good question. What would such a system look like in the laboratory?
Yeah, because it's interesting because, you know, in Steve Adler's way of trace dynamics, which we'll hear from him, classical systems, the macroscopic classical systems, are also non-equilibrium states, which are the quantum states are equilibrium states, classical states are non-equilibrium states, but quantum non-equilibrium is a different kind of non-equilibrium from the classical state non-equilibrium. And it becomes very interesting to ask, are there such systems in nature which are in a quantum non-equilibrium state?
Yes, it is very, very interesting. Yes,
no,
it's really the whole idea that we see equilibrium as a departure from non-equilibrium rather than the other way around. It's a very interesting program.
Yeah,
as I said.
David has a comment. He says, Jack Sarfati claims that a pilot wave jump could prevent relaxation in
Valentini's subquantum equilibrium. I see. Well, that claim is out there apparently. I've no idea what Mr. Sarfati might mean by it. But
my other question about Bohmian mechanics, Basil, just curious, you must have met Detlef Duer at some stage?
Unfortunately, I never met him.
Ah, okay.
I was invited to a couple of conferences and illness prevented me from going, so I never met him.
Mm-hmm. So before Detlef passed away, he and his students, Siddharth, I think, have done a lot of work on time of arrival in Bohmian mechanics and claiming that this is an experimental way to distinguish it from, standard quantum mechanics.
Yeah.
That was extremely interesting. Do you know something about this?
Yeah, I'm sorry, I don't agree with that conclusion. I worked on it in Canada with, there was a man in Ottawa. He's unfortunately, everybody I know has passed away now, which is very sad. Can't remember his name, but I worked there on a month's sabbatical, I think it was. And he was very much into this problem. And I came to the conclusion that you see, the trouble is, it depends what you mean by Bohmian mechanics. If you mean what David Bohm did, it really is no different whatsoever from standard quantum mechanics. The formalism we use is exactly the formalism of quantum mechanics. The idea that there are hidden variables, it simply means that we, instead of using Q or X as an unknown position, you say that the particle has a position.
Mm-hmm.
Now, if you're going to develop a theory of a particle having a position, and you're going to beat the uncertainty principle, for example, then you will not get the Bohm model, you see.
Mm-hmm.
The Bohm, and the Bohm model adds no new parameters in that sense, no new parameters.
Mm-hmm.
And I think that's why de Broglie didn't like the idea of hidden variables, and he didn't like the idea of the pilot wave.
Mm.
Because the particle that we're talking about is not a little billiard ball. It's part of a and as we know, when we start looking at the internal structure part, and you well know, but the only thing that we don't seem to have any structure for is the electron. But all other protons, nucleons, etc., it's a massive sea of excitations of quarks and goodness knows what else. Even the proton, I believe there's only 2% valence quarks there. And that shows us there's not something that we can get hold of. It's a process, it's an activity. And the question is, how do we deal with that activity?
Mm-hmm.
And when we come to this level, you see, how much of that do we feed in at this level?
Mm-hmm.
But that's what you're an expert in.
No. Anyway, more questions? Anybody, please?
Can I just come in very quickly to mention that David Chester has posted a clarification of his earlier report of Jacques Safatti's claim about a pilot wave pump, and he, I think he's trying to clarify that notion. He makes back reaction between the particle and the wave would lead to some framework beyond standard quantum theory. I think he's just glossing whatever it was that Safatti had in mind by saying that there was this notion that might prevent relaxation in Valentini's subquantum equilibrium. But
yeah, one more question, please, Dr. Lawson.
Sure.
I should unmute you. Yes, please go ahead.
Who's muted?
There we go. Yeah, thank you. Just the last comment about Clifford algebras and octonions.
Yeah.
We often think of non-associative products as going beyond Clifford algebras, but in fact, you can construct non-associative products within Clifford algebras. In fact, constructing the lead product for bivectors is a very useful construction. And it appears that the octonian product has also been constructed in Clifford algebras. I think De Rocha in San Paulo has done that. He's probably not the first. And I don't know if that's going to be particularly useful, but the reason it might be worth exploring is because of, I was very impressed, Professor Hiley, with what you were talking about the geometry in the quantum mechanics and how it's all really in there. And the Clifford algebra was fundamentally a geometric construction, and it's all there through classical as well as quantum mechanics. And so if it's possible to construct the octonionic product within a Clifford algebra, it may help you tie everything into geometry in a way, that can lead to insights like what you're seeing here.
Yeah, okay, great, excellent, thank you. Anthony, please go ahead, unmute yourself.
Okay, can you hear me?
Yes, now good to see you.
Yeah. Hello, Anthony. Can I say hi?
Hi, good to see you again.
Remember,
Thanks very much for the talk.
we met once in Austin, in Texas, of all places.
Yes, I remember. Okay, I'm just going to comment on what was said just now about instantiating octonions within Clifford algebra, because later in the series I'll be talking about this myself, because I found a way of getting octonions to work just in 4D in the ordinary space-time algebra, which is the Clifford algebra of 4D space. And this seems to work very nicely and leads one through to finding out that you can represent still in 4D space some of the things that has been done recently by Fury and others in terms of using octonions in the standard model. So I just wanted to say that one can certainly do this. And also on another point, you did it first, but we also have spent some time looking at twistors, again, in just 4D space and the Clifford algebra. And I think one could give a pretty full representation of that. There's a few papers from the early 2000s where we worked on this. So my message, I think, is that one really can just use 4D and the space-time algebra, which is the algebra of 4D space, the Clifford algebra, seems to be sufficient for both twistors and octonions.
So
Tony,
you could.
Can I ask Tony a question?
Yeah, please go ahead. Please go
Tony,
ahead.
where does the symplectic structure come in the work that you do, or don't you actually deal with it?
It can be represented, but we don't explicitly bring in the symplectic structure, which is interesting. I mean, obviously you think that's fundamental, but it's not something that is, that we emphasize or seem to find is the most important thing.
Yeah,
So-
I seem to find things that you guys don't find important.
So Anthony, when you bring in a SU3, say for quarks and the strong force, and you still stay in 4D space?
Yes, that's what this enables you to do. So yeah, you can represent SU3 in particular by double-sided operations of on elements of the Clifford algebra using, to surround them each side, other elements of the Clifford algebra. And this is just the ordinary space-time algebra. And I'd done that first, but I didn't understand that it's actually directly related to octonions themselves, and we're giving a little bit of the octonion product. So I'll be talking about that later.
So just to repeat the question I asked Basil, SL2O being isomorphic or homeomorphic to SO19, what does that mean really then?
Sorry, what is isomorphic to SO19?
SL2O instead of SL2C, SL2O, where O are the octonions.
Over there.
Okay, I'm not sure about that.
Mhm. Okay, no worries, no worries.
Tony, can I you made an interesting comment there again. Are you working with modules, two-sided modules?
No, it's just the ordinary Clifford algebra multiplication, which we just use either side of what
Yes, you are.
operating.
Okay, you are. In my notation, you're introducing the bimodule. Yeah, it's okay.
Okay.
It's a technical term, but I see what you're doing.
Yeah, it would
Very
be
normally
very.
that I was going to say, I mean, bimodules are, I mean, Cohn's approach non-commutative geometry. He rests the whole idea of, the map between one space and another rests on the properties of the bimodules.
Yeah, it would be very interesting to have a debate on why space-time cannot have more than 4 dimensions. I have been hearing this from many of you. Roger said that, Basil said that, and I think Anthony also means that. Can we prove that space-time cannot have more than 4 space-time dimensions theoretically or otherwise?
I know of no proof. I know of no proof. I mean, we ought to ask Roger that.
Well, Roger's arguments were all really, I mean, to me, very persuasive, but they were essentially heuristic, and they rested on the fact that you lost control of the function spaces. Your function spaces just blew up if you went beyond the 4-dimensional. That I understood him to say, and it's a pity he's not with us, but I can go back obviously and when we put his talk online in a few days. But he was said that you just didn't have enough control over the functional
But
aspect of the.
that would be probably a good theoretical argument, but from the experimental point of view, so like if I claim that the additional dimensions are there, but they are very thin, their thickness is of the order of the range of the strong interaction or the weak force, 10 to the minus 16 centimeter. They're not Planck size dimensions, but they're like 10 to the minus 13 or 10 to the minus 16. Just reinterpreting what we already know about the fiber bundle and think of it as a physical reality in terms of extra dimensions and not just a mathematical construct on the tangent bundle.
You mentioned that at the end of the discussion last week, that you should actually
Right.
we should take the fiber bundle, as it were, ontologically seriously, and I find that a
Yes.
very appealing suggestion. I mean, it just
Yeah.
I think we should see
I
that,
think
see how far we can push that.
Michael, someone said Roger's around and he wants to say something.
Oh, wonderful! I didn't realize he was with us. Okay, Roger, are you there and can you hear us?
Yeah, we unmuted him. Roger, please unmute
I don't
yourself.
see him, unfortunately, in my lineup of participants. Otherwise, I'd unmute him. If you can unmute him,
I
Tajinder.
think
I'm trying to unmute myself. Hello, can you
Oh,
hear
there
me?
he is.
Yes, yes.
Splendid, Roger.
You can hear me
splendid.
now.
Yes,
Yes.
we can hear.
Oh, okay. No, the question about dimensionality. Why do we have just 3 dimensions of space and 1 time? I mean, in string theory, they try to add a lot of extra dimensions, which somehow they regard as being too small, in a sense. I mean, the main problem is that space-time is different from these other dimensions we talk about in symmetries, because the functions we talk about are functions of 3 parameters. So you look functions of space. When you talk about a wave function in physics, you're talking about functions of 3 parameters. Now, the 4th parameter, you have differential equations, which govern how things evolve in time. But the thing is, if you try to think of space as having more than 3 dimensions, then the functions completely swamp anything you had before, so that you have an enormous functional freedom. I mean, I think Michael was indicating that point earlier. The 3 in the 3 dimensions of space, in physics that we know, we have functions that depend on 3 variables. If you introduce extra dimensions in your space, then you're in a lot of trouble. And the sort of argument that string theorists tend to use was that the dimensions are very small in a sense. But this is really a false argument, as far as I can see, because even though they may take a lot of energy to excite those extra dimensions, that amount of energy is for the entire universe. So the energy in the Earth going around the sun, for example, is enormously larger. But what am I trying to make the point here? That the energy that you would take to excite the very small dimensions in string theory is for the entire universe, whereas the energy of the Earth going around the sun is much larger than that. It's just that it's not in the right form, I suppose. But people just don't tend to consider this point. If you want to try and introduce a theory where the space-time has more, or at least the space has more than 3 dimensions, let's put it like that. If you want to introduce a theory in which space has 3 dimensions, you want it to look like ordinary physics, then you've got to have some suppression of the dimensionality of your functions, because the functional freedom for a 4-dimensional space, if you had 4-dimensional space in 1 time, so 5-dimensional space-time, then the functional freedom would completely swamp anything that we have in ordinary physics. And you'd have to explain why that extra freedom is not excited in the world we see. And as far as I know, nobody produces any argument for that. So, I mean, it's not faced up to by people who talk about extra space dimensions. So it seems to be important, if we're trying to model the physics that we know, that we have a space which is three-dimensional. Space-time can be four-dimensional. And I've always taken the view that that's very fundamental. It's not that you don't need more space dimensions. It's, if you had more space dimensions, you'd be in trouble.
So, Roger, could I ask you, thanks for your comments. Could I ask you, suppose experiments showed that there are indeed more than three spatial dimensions.
Well, what kind of experiment would you be thinking of that shows you that?
Oh, that's a good question. I don't have an answer. I was just asking, suppose that were to happen, what kind of change would that require on the theoretical side?
I'm not quite sure I understand. You see, what kind of an experiment would you say indicated that we had more space dimensions than three?
Yeah, I have been just trying to reinterpret what we already know in a Kaluza-Klein sense, that the strong interaction, say, is the Kaluza-Klein geometry of additional dimensions whose range is not Planck size, but whose range is, let's say, 10 to the minus 13 centimeters, same as the range of the force. The extent of a dimension is of the order of the range of the force.
But the range of the force, I don't quite understand.
Like suppose the strong force has a extent over to 10 to the minus 13 centimeters over e to the minus r over r naught, where r naught is 10 to the minus 13 centimeter, the scale of the force, and that is also the thickness of the extra dimensions.
But are you thinking of your fields as being functions of say four parameters?
Plus two, plus now more than four.
Yeah. No, but four parameters. You see, in ordinary physics, we consider functions which are functions of space.
Right. Yeah.
And they're functions of four parameters, of three parameters.
Mm-hmm.
And if you had functions which were more than three parameters, then the number of these functions would completely swamp the ones we see. So you have to say, why are there these extra degrees of freedom suppressed in the evolution?
Okay.
And that's not what we see in physics that we understand.
Yeah.
Now you might have a theory which did suppress these extra dimensions, or maybe they're not fully used in some sense. I'm not quite sure. See, in Kaluza-Klein theory, maybe you don't consider that the extra dimensions really behave like ordinary space dimensions in the ordinary sense.
And they do behave differently, and we have to come up with reasons why, if the universe was undergoing cosmological expansion, the rate of expansion of the extra dimensions is much slower than that of the three spatial dimensions, for some fundamental reason which one would have to come up with. Like
you'd have to have a theory why your fields are only of this very much smaller functional freedom than the fields that you would have in a higher dimensional space.
I agree. A new theory would be needed. I agree. Yes.
I mean, it's just that people don't tend to talk in terms of functional freedom. I suppose that's the reason. I don't know. But I mean, you could have a theory which has more dimensions, but for some technical reason in the theory, you suppress all functional freedoms. I don't know quite why. I mean, space has a very different role to play than these other dimensions. When people talk about symmetries in particle physics and so on,
I agree. They're
never looked at in this way. I mean, you can have more parameters in your theory. You can have lots and lots of more functions. You can have 573 functions, all of functions of three variables. But that's chicken feed compared with having functions of four variables and three variables. It's nothing like it.
Yeah. So the one kind of argument I tried to make is that the three spatial dimensions, let's say amplified by 10 to the power 60 Planck times, Planck's lengths. So that took us to the cosmological scale of 10 to the 28, 10 to the minus 33 into 10 to the 60, 10 to the 28. But there are reasons why the extra dimensions didn't grow by a factor 10 to the power 60, but by a cube root of that, which is 10 to the power 20. Now Planck length 10 to the minus 33 into 10 to the 20 happens to be 10 to the minus 13 centimeters. So if the theory allows these extra dimensions to cosmologically expand at a much slower rate than the three spatial dimensions, then we might have some way of suppressing the additional functional freedom which you pointed out.
Well, I think I'd have to see it, that's all.
Okay, thank you.
Yeah.
Yeah, I think there's a question.
Well, before you ask any more questions, I think Basil has asked me if he has obviously now been with us and talking for well over 2 hours, and he'd like just to say goodbye. Thank you. Oh, sorry, I muted myself. Could we all thank him again for a very stimulating and very far-reaching talk? And thank you again very much for all the people who took part in the Q&A, and especially, if I may say so, that exchange between you and Roger, which has been very, very illuminating. And thank you very much for everybody who's taken part. We'll say goodbye to Basil now, but we'll stay online for anybody who wants to continue the discussion for, I think we have about another 10 minutes left on the call before it ends. So
Okay.
thank you, Basil. Thank you very much again.
Thank you very much for listening, and I hope you got something from it. Okay.
Thank you.
Bye.
Thanks again very much.
Yeah. Thanks, Roger. That was very interesting. Yeah.
Wonderful. Yes, thank you. Also, thank you, Roger, very much. I'm so sorry. I hadn't realized that you were here with us because I couldn't see you in the lineup. But it's great to know that you've been following us.
No, I was here right from the start. Yes.
I do. I see. Well, I'm very sorry because of something the matter with my screen. I hadn't seen your name up there. Well, I hope to God I wasn't speaking in vain when I tried to say something about the functions blowing up uncontrollably. But I think at least I got the gist of what it seems to me. It does seem to be fairly extraordinary that we should suddenly, I mean, given how much progress physics has made for the last 3 or 4 centuries, that we should suddenly find ourselves in a landscape where there was this almost uncontrollable expansion and the loss of the constraints that we have over the size of the functions that we operate with. And I must say, intuitively, it doesn't seem to be that's a direction which could lead to any new physical insight. But who am I to judge? Anyway, it's a very interesting. We should perhaps organize a more systematic debate around the whole issue of 4 dimensions or more at some point in the series.
Yeah, I think someone said Jens had a question. Jens had a question. No. Okay, we're doing good. Yes. So maybe I could bring up Ashutosh, if you're there. You are our particle physicist here. Would you like to say something about extra dimensions from the particle physics point of view? What is your take? Not from the string theory point of view, from a particle physics point of view.
A loaded question. Well, what can I say? So there was a while, early 2000s when the theory literature exploded. That theory literature, after a while, turned into a bunch of sort of Monte Carlo-like models of various kinds of extra-dimensional signatures, from heavy graviton states, Kaluza-Klein modes of gravitons, then Kaluza-Klein modes of other things. when people said they may be more universal than initially thought. So the whole thing became universal extra dimensions. And then, so the Kaluza-Klein mode search is expanded beyond gravitons to modes of Z's and W's and everything else. So the general logic was that the gauge quantum numbers would be similar. So the couplings would be, that's how I understand it, that in all of this logic, either it's universal coupling, like graviton should have universal coupling, energy momentum coupling, or for whatever other reason, it preserves the original standard model gauge coupling. So under these assumptions, if it was some colored thing because it's the Kaluza-Klein mode of something colored, then the QCD calculation rates are believable because you know the QCD coupling. Or if it's a Kaluza-Klein mode of WZ, photon, whatever, then you have the reasonable sounding assumption that those gauge couplings will carry over. In other words, in all of those things, the mass and the width of the new state was variable, but couplings were one way or the other not variable. They were assumed to be predicted because that's the model. Well, then at the end of all that, none of that has shown up. So then, go ahead.
No, to answer what Roger asked, what kind of experiment would confirm extra dimensions? And if you have any thoughts about what Roger's saying, that if you introduce extra dimensions, you have too much functional freedom, and that's a problem.
Problem for whom? Experimentalists don't care about your freedoms, right? You guys may have trouble controlling the freedom, but what do we care?
I agree.
So in some sense, more freedom to you means more possibilities for us to probe and either find or refute.
The problem is, what kind of fields are you talking about? I mean, it's quite different to consider a theory with more parameters. I mean, you can consider fields where you have more and more components. You can have, as I was saying before, 5,000 components, but they're still only functions of 3 variables. If you change the functions of 4 variables, you're entering into a new universe. I mean, a new concept altogether. It's not the physics we know. You have to have some reason for suppressing.
Where's Jens?
All the freedom which is in these functions. Why don't you see it in the world? We don't see it. We see a freedom which is functions of 3 variables.
That is true. So in my particular field, which is high energy collider physics, in the end, our sensors are only sensing the usual energy deposition signals. So in this sense, we are not in the business of, of exploring systems with multiple states and then somehow additional states are showing up. That's what am I trying to say? If there is some system where, like, what are the fundamental freedom? If that's the kind of logic, like quark-gluon plasma, if you're saying something like the creation of the quark-gluon plasma implies that there's a transition from the hadronic degrees of freedom to the quark and gluonic degrees of freedom, and you have some statistical ensemble of the new degrees of freedom, and they say that they can see the evidence of that, the transition from the old degrees of freedom to the new. If you're implying something like that, you need a statistical system. And
David,
we don't make statistical systems in collider physics. Am I understanding your point?
David.
Sorry, Tajinder, I do apologize for intervening, but I'm afraid we are just about to come to the end of our allotted time. the Zoom connection ends at 2.5 hours.
David.
We're now only about 2 minutes away from that. So this has been an utterly fascinating
David.
day.
There's a question, Samuel. Who, buddy? You
Well,
want to say
okay, but
something?
there may not be
Yeah.
time to ask it. We
You
may
can
just
call me, buddy.
letting you know. We may be cut off at any moment.
Okay,
Who's
so
the
maybe-
gentleman who wants to ask the question?
Me. I
Oh,
have
go
a
ahead,
question.
please.
Go ahead.
I have a question for David.
Who is David here?
David Chester.
Oh, he's here. Oh, David is there. Yes, yes. Go ahead. Go ahead.
Do you play Stumble Guys? Is that a yes or no?
I don't know. What's the question? I don't get the question.
I'm muted. Yeah, you can unmute yourself. It's no problem.
David, what's the question to you?
Sorry, I didn't hear the question.
Oh, it's okay. It's okay.
Okay.
Okay,
You
Michael,
can
you
ask if you'd
can.
like, or I don't know.
I think we're going to have to
But, yeah,
call
well-
it a wrap, I'm afraid, because we're
I know,
about
I'll
to
be
lose
around in the future, so
connection.
don't worry about it.
I'm sure you guys can email, and maybe we're going to put up a blog alongside the YouTube record of the talks. We're also going to put up a kind of discussion chat forum. So if you guys want to continue to message either one-on-one or to the group as a whole, you'll be able to do that in a few days. Okay, so we'll look forward to the next talk, which is on the 24th, I think.
Yes, yes.
And can you remind me? I'm sorry, Tajinder, I'm afraid
Yeah.
I've forgotten
I'll
who our
be-
speaker
I'll,
next time is going to be.
So this will be Albert Schwartz from UC
that's-
Davis.
That's
And
right.
that will be a very interesting introduction to Jordan algebras, quantum mechanics, and particle physics. The role of Jordan algebras in quantum theory and particle physics. That should be very interesting, yes.
Excellent note on which to end. So once again, thank you very much to everybody, Basil and all of the participants. And thank you again. We'll see you
Thank
all
you.
again, I hope, in a couple of weeks.
Thank you, Michael. I love you.
Oh, thank you, Guy. Thanks. Wow.
Thanks to the organizers for this
Thank
lovely
you.
discussion.
Take care, man.
Thank you, thank
That's
you,
great.
bye-bye.
Look after yourselves. Take
Bye,
care.
David.
Bye-bye.
See you next time, bye-bye.
See you soon. Okay, cheerio, Tajinder. See you soon.
Bye, Roger.
Thanks to Roger especially. Bye. Take care.
Bye-bye.
W Roger in chat. Yo, Roger, you're still here.